Greetings, everyone. All right, let's do some calculus on some parametric equations. And the first question naturally that should come up in your mind is what about slopes? Because that's where we started the calculus class with, and using a regular function notation and regular types of functions. Now, how do we find the slope of a curve defined by a set of parametric equations? All right, let's go through that. So let's start by letting x equal some function of t, y equal some function of t as we defined a set of parametric equations. And let's define a third thing. Let's let y equal some function h of x. So we don't have the direct, we're doing this in general, so we don't have a direct equation, but we talked about converting a pair of parametric equations to a standard function. And basically that's what we're talking about here. But let's identify this over here. This is really just a composite function. We have our outer function h, and we have the inner function x, which is a function of t, as defined back over here. So when we work this out, we're going to have to think in terms of a chain rule application, okay? Now, both x and y are functions of t. Okay, so we're going to differentiate y equals h of x with respect to t. And so let's take the derivative with respect to t of h of x. Now, of course, we'll take the derivative of the outer function, which is going to be h prime, evaluated at the inner function, and then we're going to multiply by the derivative of the inner function. And I'm going to write that, since we're doing this with respect to t, dx over dt. Now we can also write this slightly differently here. I can write this as dy over dt is equal to, now h prime, well, h is equal to y, so h prime is going to be equal to y prime. Now we're doing y is equal to h of x, so we'd be differentiating y with respect to x, but applying the chain rule over here. Okay, so dy over dt would be equal to dy over dx, excuse me, times dx over dt. And then if we were to solve this for dy over dx, this would give us dy over dt divided by dx over dt. So in other words, if we want to find the slope of the graph of a set of parametric equations, in the xy plane, the slope given by dy over dx is going to be take the slope, or rather, I'm sorry, the derivative of the function y with respect to t and divide that by the derivative of x with respect to t. Now, all this, of course, is true as long as dx over dt is not 0, and we have to consider that every time we take a derivative, or rather have a quotient. We don't want the denominator to be 0. All right, so how about a first example here? Let's find dy over dx if x is equal to 3t and y is equal to 2t squared. All right, you should pause the video and go do that really quickly, but I'm going to jump right into it. So remember, we're finding dy over dx, and as we just saw, that's going to be dy over dt divided by dx over dt. And dy over dt is just taking the derivative of y with respect to t. That's 4t. Derivative of x with respect to t is just 3, so this is really just 4/3 times t. You don't have to rewrite it if you don't want to. It's the same thing. Let's go take a brief look at the graph of this. In fact, I'm going to pause and set it up. All right, so you're looking at the graph. It's just a parabola. No big surprise there, I wouldn't think. I do have a point moving along the parabola, so you can see the orientation. Remember, the orientation is the direction the graph is traced out as the parameter increases. And what I'm going to add to the graph right now is the tangent line. Now, if you look at my tangent line equation, I got this g of a. G of a is just the 4/3 t, or rather g of t is 4/3 t. That we calculated for dy over dx. So g of a is just that expression evaluated at all these different a's. So in other words, it's the slope of the tangent line. And then I just wrote the equation of the tangent line in the usual way. The slope, in this case I called it g, so it's g of a, times x minus the x coordinate. The x coordinate is not 3t because the point is at 3a and I have to evaluate it at that point. So it's x minus 3a plus 2a squared, and it lands perfectly tangent to the curve. So to find the slope, do this dy over dt divided by dx over dt, plug in a particular value for t, so you get that corresponds to a particular point on the graph. That'll be the slope at that point, and then you can write the equation as illustrated. All right, let's go do another example. Example number 2. Same thing, we're going to find dy over dx if x is equal to t squared times e to the negative t, and y is equal to t times the natural log of t. So take a moment, pause the video, go work that out for yourself. Hopefully you're able to do so on your own. So remember, I'm just going to keep writing this down so it drills it into your memory here. dy over dt divided by dx over dt. dy over dt is going to be, now don't forget the product rule here. Hopefully you remembered that. Derivative of t is 1 times the second factor plus the derivative of the second factor, which is 1 over t times the first factor. Now you can simplify that. 1 over t times t is just 1, of course, but I'm going to leave it there for now. Derivative of t squared is 2t times e to the negative t, and then we're going to get a negative t squared e to the negative t. That subtraction is coming from the derivative of e to the negative t. Applying the chain rule, the derivative of negative t is negative 1, so that's where that negative is coming from. So if you want to simplify this, you can, and you could have natural log of t plus 1 divided by 2t e to the negative t minus t squared e to the negative t. Pretty straightforward. So when we're finding dy over dx here, it's not a quotient rule problem unless x of t or y of t happen to be quotients, but in general, this is not a quotient rule problem. We're just going to take the derivative of the y coordinate with respect to t and divide by the derivative of the x coordinate with respect to t. All right, I think I'm recording. All right, so here is the graph of that. It's in blue. You can see the parametric expressions here as an ordered pair in Desmos in terms of t. That's how you can graph those. I used 0 to 10 for t. I use a parameter b so that I can let b change, and we can see just an isolated point move along the curve. I defined the slope, I called it m sub 2 as the value that we just calculated, and then y equals the slope at b times x minus the x coordinate at b plus the y coordinate at b. And if I graph that, you could see the tangent line propagate around the curve. So hopefully that is something that's understandable. So we can still write the equation of the tangent line. We can still find the slope. All of that should be pretty straightforward stuff. Just applying our new skill of finding the derivative of a set of parametric equations, or rather dy over the expression for dy over dx for a set of parametric equations. What about higher order derivatives? Meaning, what if we want to take the second derivative? Well, notice that dy over dx back up here when we were calculating it, it's a function of t. Okay, in all of these examples that we got, the answer is in terms of t. So if we want the second derivative, we're going to have to take the derivative with respect to t. So d by dt of dy over dx. So if we apply that to h prime of x, of course that would be h double prime of x times dx over dt. So h double prime of x would be equal to the second derivative of y with respect to x by definition. Now I'm going to take this expression over here, or this equation, this equal to this, and I'm going to solve it for h double prime. Okay, I'm leaving out the middleman here, but we're going to solve that. So it means I just got to divide both sides by dx over dt. So this is d over dt of dy over dx divided by dx over dt. So I just did some division right there. So what is this telling us? Well, if I have the first derivative, I'm going to take the derivative of the first derivative with respect to t. That's going to require the quotient rule. And then I'm going to divide that result by dx over dt. If that's confusing, don't worry about it. I'll show you an example in just a moment. If we were to do this again, it would look like this. So the derivative with respect to t of the second derivative of y with respect to x, we'd be taking the derivative with respect to t of h double prime of x, which would be h triple prime of x times dx over dt by the chain rule. And so h triple prime of x would be equal to, well, that's our third derivative of y with respect to x to follow our pattern. We'd take the derivative of the second derivative, which is still a function of t. So we take its derivative with respect to t, and again divide by dx over dt. And then we would just continue that pattern. All right, let's actually try this for the previous examples. So let's say, call this example 3. Find, I'm just going to do the second derivative. I've never seen them ask for a third. Find the second derivative of examples 1 and 2. All right, you should probably pause and go try these out. But for example 1, we had dy over dx. That was equal to 4/3 times t. So if I want the second derivative, excuse me there. If I want the second derivative of y with respect to x, as it says above, you're going to take the derivative of dy over dx with respect to t, and we're going to divide that by dx over dt. Well, the top part, the numerator, means I just got to take the derivative of dy over dx. That's 4/3 t with respect to t. Well, that's easy. That's just 4/3. And then we have to divide that by dx over dt. And if you remember, dx over dt way back up there was 3. So this works out to be 4/9. What about in example 2? In example 2, we had dy over dx equal to, I'm trying to remember now, I think it was the natural log of t plus 1, and then in the denominator we had 2t e to the negative t minus t squared e to the negative t. This one is going to be, well, brutal? I don't know. It's going to be more challenging. We want our second derivative of y with respect to x. So I'm going to take the derivative with respect to t of dy over dx, which is going to be a somewhat nasty quotient rule problem, and then I got to divide that by dx over dt. Whoops, not dx over dx. dx over dt is right there, so you might want to just remember where it is so it's easy to go find later. All right. I'm not going to do much simplifying for this one, but let's work this out. So I'm differentiating this expression here with respect to t, and I got to use the quotient rule because it is a quotient. So low d high, and the derivative of high is fairly easy right there because it's just 1 over t plus 0 minus high. Use parentheses, ladies and gentlemen. D low, this is where it gets a little bit ugly, I guess. So I got a product rule here, so 2 e to the negative t. and then minus 2t e to the negative t, and then minus parentheses 2t e to the negative t, minus t squared e to the negative t. So that's low d high, I'm just checking everything, minus high d low, all divided by low squared, so 2t e to the negative t minus t squared e to the negative t, and then all of that divided by dx over dt, which, whoops, I said that's squared, which is another factor of 2t e to the negative t minus t squared e to the negative t. Now, I'm not going to simplify this. I don't care to. It's not the point. The point is, could we do it? Yes. Well, I don't know how much we could simplify it, but we could at least get this far. This term here is going to end up in the simplification if we were to do it as one more factor in the denominator. So we'll end up with it being cubed in that denominator. And I'm not sure anything cancels. We couldn't cancel this term with one of these because of the difference here, unless this simplified in a way that would help us out. But I don't know if it does because I didn't try it. And that's not the point. Okay, the point is we just found the second derivative because we were asked to do so, and I'm not going to simplify it. So here's another problem. So find an equation of the tangent line at the points given there for the parametric equations x equals 2 minus 3 cosine theta and y equals 3 plus 2 sine theta. You may want to go at least start it on your own before you start listening to me, but I am going to jump right into it. So pausing for a moment, at least thinking about some of the steps you might do for this would be helpful. Here's the graph, okay? So I just typed in, remember in Desmos you want to use t instead of theta. So 2, make sure I typed this in correctly. Yeah, I did. Okay. So it's an ellipse, okay? So be it. I have the points here, but I'm not going to plot the points yet because I want to generate some results from doing the calculus first. So we'll take a look at that in just a moment. So dy over dx. That is sloppy. All right, so this is going to be dy over d theta, since everything's in terms of theta, divided by dx over d theta. And so dy over d theta is going to be derivative 3 is 0, so this is going to be 2 times cosine of theta. And then this derivative of 2 is 0, derivative of cosine is negative sine, so we're going to get a 3 sine theta here, okay? So from here, let's go take a look at what's going on for just a moment. Okay. At the point -1, 3, we have to remember some things. We have to remember that our x-coordinate is -1 and our y-coordinate is 3. That's not directly represented in our slope right here, but I know x is equal to this and y is equal to this. So what I'm going to do is I'm going to take -1, since that's x, and set that equal to 2 minus 3 cosine theta. And then I'm going to take the 3 and set that equal to 3 plus 2 sine theta, since that's the y. And then I'm going to go look for solutions for this. So if I subtract the 2, I get -3 is equal to -3 cosine theta. So that means cosine theta has to be equal to 1. And we should know that that's going to be equal to, for values of theta equal to 0, 2 pi, 4 pi, and so forth on down the line. In one revolution, just 0 and 2 pi. Now what about this one over here? If I subtract the 3, I get 0 equal to 2 sine theta. So that means sine of theta is going to be 0. And that's for values of theta that equals 0, pi, 2 pi, 3 pi, and the negatives as well. And we can go negatives over here as well, but we're just looking, basically we need to get around the ellipse just one time. What we care about here are the points that we have in common, okay, from the two sets of solutions. So what do we notice from these sets of points, okay? Dy over dx, Well, actually, hold on real quick. What do we have in common? We have 0 in common. We have 2 pi in common. That's on both. So is 4 pi, but I only need one revolution, and that's going to 0 to 2 pi is going to get me around the circle just once. So what's happening to dy over dx at these values? So at theta equals 0, what happens? Well, at theta equals 0, that means our denominator is going to be 0. So this does not exist. Same thing if I let theta be equal to 2 pi, because at 0 and 2 pi sine is 0 both times. So that does not exist. So what does that tell us? That's right. That means we have a vertical tangent line there. Let's go take a look at the graph. Remember, when the numerator is not 0 and the numerator is not 0 at 0 and 2 pi, okay, again, I look at the values that they have in common. The numerator is not 0, but the denominator is. It means that's telling us that we have a vertical tangent line happening there. So if I go back over here to the graph and turn on this point, negative 1, 3, you can see that that line, that point is at the edge right there. And if I type in x equals negative 1, then the tangent, that is the tangent line right there. So the equation of the tangent line here is just x equals 1. I should have answered the question before doing that. I'm sorry, x equals negative 1, because when the tangent line is vertical, that means it's going to hit the x coordinate of the point of tangency, and the x coordinate is negative 1, so it's x equals negative 1. I hope that made some sense. Pause the video and go work on what happens at the next point on our list, 2, 5. I'm not going to pause, though. I'm going to keep going. You should, like I said, pause and go figure things out. So we're going to have 2 is equal to 2 minus 3 cosine theta. And 5 is equal to 3 plus 2 sine theta. So here we're going to get 0 equal to negative 3 cosine theta, or in other words, cosine theta has to be equal to 0. Let's just worry about one revolution. That's going to be at pi over 2 and 3 pi over 2. Over here, when I subtract 3, I get 2 is equal to 2 sine theta. So that means sine of theta is equal to 1. Sine of theta in one revolution is equal to 1 when theta is equal to pi over 2. And so our common angle that we have in our solutions here is pi over 2 in our single revolution around the unit circle. So what happens to the slope when we evaluate that at pi over 2? Let's go take a look up here. Well, at pi over 2, we know sine of pi over 2 is 1, and cosine of pi over 2 is 0. So I get 0 in the numerator and 1 in the denominator. So this is 0, which tells us that the tangent line is going to be horizontal, and horizontal lines are going to be of the form y equals the y coordinate of that point. So our tangent line is y equals 5. If I turn on this point here, you can see it's at the very top of the ellipse. And if I type in y equals 5, you can see there's our tangent line at that point. Now I'm going to turn on the other point. It's not one where the tangent line is vertical or horizontal. It's over here, so it's a little different than the other examples, but you should go check that one out and see what you come up with. Okay. Now I'm just going to get started here. So at 4 plus 3 root 3 over 2 comma 2. So 4 plus 3 root 3 over 2 is equal to 2 minus 3 cosine theta, and then 2 is equal to 3 plus 2 sine theta. Oh, so now I got to subtract 2 from both sides, but 2 is 4 over 2, so maybe you could see that this is going to be 3 root 3 over 2 when I subtract 2 from both sides. If you can't, I'm not sure what to say. It's just arithmetic. No. Just find a common denominator and you can work that one out for yourself. So we're going to divide both sides by negative 3, so that the 3 will cancel here, and I'll be left with negative root 3 over 2 is equal to cosine theta. And we should be able to figure that out. I'll do that in a moment. Let me fill in this space here real quick. So this, when I subtract, is going to be negative 1 equal to 2 sine theta. So sine of theta is going to be equal to negative 1/2. All right, now that we have those two values, this one over here, cosine is negative in quadrants 2 and 3. From our special right triangles, our 30, 60, 90 right triangle, the reference angle here is going to be pi over 6, because the cosine of pi over 6 is the adjacent, the long leg of the 30, 60, 90 right triangle divided by the hypotenuse. So that gives us the root 3 over 2. And so the angle theta here, we'll take pi minus pi over 6, so that's 5 pi over 6. Pi plus pi over 6, that's 7 pi over 6. I'm going fast here. This is trig. I know it's probably not that fresh in your mind, but do the best you can. Or come by and see me for a little extra trig reminders. For sine equal to sine of theta equal to negative 1/2, negative in quadrants 3 and 4. The reference angle for sine is going to be also equal to 1/2, is also going to be pi over 6. And so the angles here are going to be 7 pi over 6 and 11 pi over 6, but the one that they have in common is going to be the 7 pi over 6. So that's the one that we're going to use. So our slope, dy over dx, evaluated at theta equals 7 pi over 6, is going to be, I don't remember what the derivative is, 2 cosine theta over 3 sine theta. So it's going to be 2 cosine of 7 pi over 6 divided by 3 sine of 7 pi over 6. Notice we're talking about a third quadrant angle, and both sine and cosine are negative in the third quadrant, which means this ratio is going to end up being positive. Cosine of 7 pi over 6 is going to be negative root 3 over 2. We already found that. Sine is going to be negative 1/2, going back to what we had up above. And so when we work this out, I'm trying to figure out the best way to simplify this. This is going to be negative 2. No, it's going to be positive because the negatives are going to cancel. It's going to be root 3, 2 root 3 over 3. Yeah, 2 root 3 over 3. All right, so how do I write the equation of the tangent line? So that's going to be y equals the slope, 2 root 3 over 3. Now remember the coordinates of the point were the coordinates of the point were 4 plus 3 root 3 over 2, comma 2. So x minus 4 plus 3 root 3 over 2 plus 2. There's the equation of the tangent line. Let's go type that in and see if it actually is tangent to the curve. So y equals 2 square root 3 over 3. Is that what I said? Yeah. Times x minus 4 plus 3 square root 3 over 2. I know you're probably saying, why didn't you just type this in before? Because I didn't. But notice it's beautifully tangent to that curve, just as we wanted it to be. All right, what about arc length? Way back when we learned about arc length, we said arc length on the interval from a to b for, just a regular old function was this. That's f prime of x with respect to x. And we did a lot of work developing that. The development that we did for that, which I'm not going to take the time to go through here, can be used to generate what we need for a set of parametric equations, but I'm just going to jump right into it. If our parametric equations are, x equals f of t and y equals g of t, I'm going to give it to you a couple different forms. Then the arc length is going to be the integral from a to b of the square root of f prime of t squared plus g prime of t squared, the square root of all of that, and then all with respect to t, or you can do the integral from a to b of the square root of dx over dt quantity squared plus dy over dt quantity squared, all with respect to t. Now, A and B are t-values, okay? So the t-values that put you at one point, starting at one point, ending on another point on the curve, okay? So this is a pretty straightforward formula that you should just learn. And again, it follows directly from what we did before. We can talk about it some other time, but in the interest, this video is over 34 minutes already. So let's find the arc length for that previous example, the loop. Find the arc length for the loop in the previous example. All right, so what are we talking about? It's this one right here. Let me zoom back out. So talking about this loop right here, and we know the t-values that get us here because the two t-values, one of them is going to be negative root 3 and the other is going to be positive root 3. They get us to that point. So one, we come in, I think, this direction here, and if I'm wrong, it's the other way, but it's not that big of a deal. And it say negative root 3 puts us here, and then at positive root 3 it'll put us here, and then goes off. So I want from negative root 3 to positive root 3. And so you should probably pause this and try to write it down, but our arc length S from negative root 3 to root 3, and then I'm going to take the x derivative, or the derivative of x with respect to t, which I don't remember what that was right now, so I'm going back to where that's 3t squared minus 3 quantity squared plus 6t, that's dy over dt, quantity squared, and then we'll integrate that with respect to t. You can go plug that into your calculator and you're going to get 20 point something. I don't remember. It doesn't really matter. I'm trying to keep the video at this point. I'm trying to end the video at this point, but as long as you can understand or remember that formula and then just use it and then use a calculator to generate the values, you're good to go. Go study.